These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos by making a monthly pledge at my Patreon page. Or you can make a one-time payment by using the PayPal donate button on my website. Thank you. So this is a unit of measurement. What concept is measured with this unit?
Volume.
Yeah. What's the typical abbreviation for this for liters?
Capital L.
Okay. And volume is a measure of how much space something is taking up. So this is one of the units that was used in the practice problems that you sent me. That's pretty straightforward. Here's another unit that's in those practice problems. This is a little bit harder to define. What's a mole? What do moles measure?
Is it the amount of something?
That's a good answer. Yes, it's a measure of the amount. Well, what does that mean, the measure of the amount? Really, it's just a measure of the number of items. As you should have learned when you took your general chemistry course, the word mole is like the word dozen. It's just the name for a number. Dozen just means 12, and mole is just a number. Do you remember what number a mole is approximately?
Was it Avogadro's number?
That's right. Do you remember what that number is? Like a dozen is 12. Do you approximately remember what a mole is?
No, not off the top of my head.
Is it a big number, an ordinary number, or a small number?
Like a very small number.
So you're saying that the mole is a very small number?
Mole.
Is that right?
No, I think it's a very big number.
Yeah, your second answer was better. A mole is about 6 times 10 to the 23rd, which is a huge number, 6 followed by 23 zeros. Why did you say it was very small? What made you think of that? Well, what types of things would you have to count in moles? Would you usually count big things in moles or small things in moles?
Small things in moles.
Because otherwise, how could you get that many? Yeah, you're never going to have 6 times 10 to the 23rd cats because you wouldn't have a big enough space for them, right? You can't count 6 times 10 to the 23rd pickles because there wouldn't be enough room for them in your kitchen. The only thing that you could have 6 times 10 to the 23rd of is things like atoms and molecules, things that are so tiny that you can fit a huge number in an ordinary space. So you probably said it was a very small number, not because it is a very small number, but because it's used for counting very small things. Like you need very big numbers to count very small things. For example, how many grains of sand are there at the sea? How many grains of sand are there on the beach? Well, I don't know, but it's a very big number because the grains of sand are so small. Okay. All right, so we need to remember from our chemistry course that this is what a mole is. So it's a measure of the number of items, like the word dozen is. Do you remember what the abbreviation for moles is?
Lowercase m.
Like this?
M-O-L.
That's right. Actually, lowercase m is molality, which probably won't be too important in your course. So moles is M-O-L. It's kind of a weird abbreviation because it's hardly any shorter than the word is. But anyway, we don't use lowercase m. We use M-O-L for moles. Okay. So again, that's another of the concepts that you need in the practice problems that you had sent me. So let's move on to the next concept. The next concept is molarity. Now, liters measure volume, moles measure number. What does molarity measure?
Moles.
So you're saying the molarity measures the number of moles?
Yes.
Now, in that case, it would be pretty much the same thing as moles. It wouldn't be a different thing.
Yeah.
Actually, molarity is different than moles. It's kind of unfortunate that they use two words that sound so similar, but they actually mean different things. Molarity is a measure of concentration, which is very different than the number of items. So the molarity measures the concentration, not the number of items. Okay, so this is one of the most important concepts in the practice problems, so let's make sure we're clear about this. Let's see here. First of all, do you happen to know what the abbreviation is for molarity?
Capital M.
Capital M. Sometimes molarity is just referred to as molar. And for even shorter, it's capital M. So it's very important not to confuse moles and molar. They sound very similar, but they're totally different. Now, molarity actually is has subunits. You can break it down into subunits. Do you know what the subunits are for molarity? When we say something is, say, 3 molar, what does that mean?
Can you break it down to millimoles?
Let's see. That doesn't sound like the right track, so let me help you with that. Capital M, molar, stands for moles per liter.
Okay.
Molarity stands for moles per liter. Hopefully now you can start to see how that's a measure of concentration. In fact, when I told you it was a measure of concentration, maybe we should have been able to figure out that these would be reasonable units. Okay, so again, notice there's a huge difference between capital M and MOL. Capital M is MOL over L, moles per liter. It's a measure of concentration. Concentration basically means crowding. It tells you how, so we're usually going to apply this to a solution, such as your blood. Your blood is a solution, and there's lots of stuff floating around in the blood, and we want to know how crowded those solutes are in the blood. So, for example, suppose we have a solution that is 3 molar chloride. What does that mean? It's very important to understand what this means. This means 3 moles chloride per liter of solution. So these are very important concepts to have in your notes. Notice we don't write chloride on the bottom of the fraction. Something that's very important in chemistry is to focus not just on the units, but the substance. Well, the substance on top here is chloride, but the substance on the bottom is just the whole solution, the whole liquid solution. So 3 molar chloride means 3 moles of chloride per liter of solution. Now, how do you interpret that? What does that mean? What does this fractional unit mean? I think this is something that maybe we worked on when we were working on physics. I think we talked about how to interpret fractional units. We said if you're trying to interpret fractional units, the best thing to do is write the whole number as one fraction and then put a number on the bottom. What number can we put on the bottom of this fraction that doesn't change the value of the fraction? I'm sorry, did you say something? What number could we put here?
1.
That's right. So what does this mean? What does this tell us about the solution? It means that if we took 1 liter of the solution, there would be 3 moles of chloride in it. Does that mean we actually have 3 moles of chloride? Well, no, because we don't necessarily have 1 liter of solution. It's hypothetical. If we took 1 liter of the solution, there would be 3 moles of chloride in it. So that's how to interpret this. This is telling us how crowded the chloride is. It doesn't tell us how much chloride there is, but it says that in every 1 liter, there's 3 moles of chloride. So this is an important concept. Let's make sure we understand it. So what does it mean if we have a solution that's 2 molar sodium? So how would we break that down into subunits? How would we break the capital M down into subunits?
You have 2 molar Na plus over 1 liter solution.
Like this?
MOL.
Yeah, so what you said was incorrect. You said 2 molar. But remember, this is molar over here. So we don't want to confuse molar and moles. We have 2 moles of Na plus over 1 liter of solution. It's important not to confuse those two concepts. Okay, does that mean we actually have 1 liter of solution?
No.
No, it just means that if we took our solution and we poured out 1 liter, there would be 2 moles of Na plus in it. Suppose that we poured out 3 liters of solution. How many moles of Na plus would there be?
6.
Good. So notice this doesn't tell us the actual number of Na+. It doesn't say that we actually have 2 moles. We'd have to know the volume to know that. It just tells how crowded the Na+ is in 1 liter.
So the moles is measuring the amount of atoms, basically?
Yes.
Or the amount of something?
It's the amount of something. The word that you use for the something depends on what type of thing it is. Remember that you could talk about the number of moles of cats or the number of moles of pickles. You could talk about the number of moles of atoms or the number of moles of molecules. In this case, the correct term is ions. Here we're counting the number of moles of ions because these are not molecules or atoms, they're ions. So yeah, a mole measures the number of individual items, and you have to put in the right word for the type of items that you're talking about. So in this case, we don't know how many moles of sodium ions there are, but we know that if we took 1 liter of solution, there would be 2 moles of sodium ions in it. Okay, so this is going to be a really crucial concept in this chapter and probably throughout the text as well. The big lesson here is don't confuse moles and molar. They're very different things. Okay. So to review, molarity is a measure of what?
Molarity is the measure of moles per liter.
Those would be good subunits. That's right. Good. It measures moles per liter, but what concept does it measure? For example, liters measure volume, moles measure number. What does molarity measure?
Concentration.
It tells you how concentrated the solution is. That's right. Another word for molarity is molar, remember? And what's the abbreviation for molarity?
Capital M.
Remember, to be more specific, molarity is moles of solute particles over liters of solution. Okay? Do you know what these brackets mean? What does this symbol mean?
Is it the element in its basic form?
You said in its basic form? Okay.
I mean, normal. I don't really know.
Okay, you might not be sure. This actually means, the brackets mean the concentration of.
Okay.
Brackets mean, this is a symbol that's used in your textbook in chapter 2. The brackets mean, and this is a standard symbol in chemistry, the concentration of. The concentration of what? The concentration of whatever inside the brackets. So, for example, this symbol means the concentration of potassium ions. So how would you read this symbol aloud in words?
The concentration of calcium ions.
That's right. Okay. So what units would we measure the brackets in?
In molarity.
That's right, in molarity, because it's concentration. So for example, we could say that this was equal, just to make up a number, we could say this is 0.7. What's the abbreviation for molarity?
Capital M.
So we could write it like this. The concentration is 0.7 molar. Now remember, in chemistry, oftentimes it's best to also write the substance. So maybe it would be better to say 0.7 molar Ca2+. All right, so when we see brackets, this is measuring concentration. Notice this does not measure the number. It doesn't tell us the number of items, just the concentration or crowding. Now, let me point out a mistake that I see people make a lot. So the way I have this written here, and this is the correct way to write it. A mistake that I oftentimes see students make. Can you see that this doesn't make any sense? Because remember, brackets mean the concentration of. Well, it's meaningless to say the concentration of 0.7 molar. That is just a meaningless statement. So it makes sense to talk about the concentration of calcium. The concentration of calcium is 0.7. It doesn't make sense to say that the concentration of calcium is the concentration of 0.7. So the point I'm making is never write a number inside the brackets. That's a common mistake. We never write a number inside the brackets. What do we write inside the brackets? The name of an ion or a substance. But we don't write a number inside the brackets. Okay. Okay, so now I want to start working on quantitative problems to start working up to the types of problems in the practice problems you sent me. So here's a quantitative type problem that you might have to do, might have to work through. Tell me when you have this written down.
Okay. Okay. So concentration is measured by by molarity. And molarity is moles over liters, and we're given moles and we're given liters, so I would just put 0.06. Actually, at first I would put brackets around K plus, and then I would have 0.6 over 3.7.
Go ahead and just keep continuing until you're finished.
And I get 0.162 mole. 0.162 molar.
Okay. That's good that you were thinking about the units for your answer. Okay, so it's always good to start by identifying the question. The question here is asking us for the concentration. What are the units for concentration?
Moles per liter.
Right, or molar. So that gives us a guide to how to work this out. We just have to put numbers on the top and the bottom here. Well, we could put 0.6 moles of potassium. We could say that what we're trying, so actually the best symbol, I think you kind of said this, what the question's asking us for is this. This is a good symbol for what the question's asking. So this would be 0.6 moles over the 3.7 liters of solution. And what was your answer?
I got 0.162 molar.
Okay, good. Or better, 0.162 molar potassium. It's good to include the substance, but that's good. Okay, so you figured it out. That is the correct way to solve this problem. By the way, now you can see why we started the session by going over these units, because the trick that you used for solving that problem was thinking about the units. Why is this important for your biochemistry course? Well, biochemistry is basically just about the solutions inside your body. The solution, so the cytoplasm in a cell is a solution, and the blood in blood vessels is a solution, and there's lots of stuff floating around in the cytoplasm or the blood, and we analyze that in terms of concentration, like we've been doing here. Okay, so that's correct. All right, that's good. Okay, well, tell me when you have this problem written down.
Okay.
Okay, well, now it's time to try the problem. So again, try working the problem out on paper, and please tell me what you're writing down as you go so I can make sure we're on the right track.
So first I would write bracket chlorine, end bracket, 0.62 over 4.8 moles of as well. I would not write that. I would write 0.62 is equal to x over 4.8. Multiply both sides by 4.8. And I get 2.98 moles of chlorine.
Okay, so a good place to start is to write down what the question is asking us for here, which is the number of moles of chloride. You got off on the wrong foot, but then you caught yourself, so that was good. At first, you were treating this as if it was the same as the previous problem. At first, you were treating this as if it was the same as the previous problem, but then you had second thoughts and you saw it's actually different. In the previous problem, I gave you moles and asked you for molar. But in this problem, I've given you molar and I'm asking for moles. So it's good that you were careful about that. So we could take this information here. We know that we have 0.62 molar chloride. And we could write that as an equation. This tells us that hypothetically, if we had 1 liter of solution, there would be 0.62 moles. But we know that we actually have 4.8 liters of solution, and we're trying to figure out x, the number of moles. And then you solve this equation. Okay, perfect. So that would work. Again, you can kind of use units for this. Let me show you one other way that I prefer for this type of problem. I prefer to kind of do this as a unit conversion. Like, I think we worked on unit conversion for your physics course. What would be the target units here?
The target units would be, we want to get moles.
Good. Better to put the substance too, moles of chloride. And then remember when we worked on our unit conversion, we have to write down our starting information. So what piece of information are we starting with here?
We have 4.8 liters and 0.62 molar.
Now this is what I would call the starting information. Remember, we also need a conversion ratio. So the key thing is anything that has fractional units can be used as a conversion ratio. Anything with fractional units can be used as a conversion ratio. Well, molarity has fractional units, so it can be used as a conversion ratio. In fact, it gives us two different conversion ratios. I think we talked about that in the summer physics course. This is 0.62 moles over 1 liter. And it's also 1 liter over 0.62 moles. Those are the two conversion ratios we can get from that. So which of those would be helpful to write here?
0.62 moles of chloride over 1 liter.
Because then the liters cancel. So now what?
You multiply across.
Okay, go ahead and do that and tell me what you get.
I get 2.98 moles of chloride.
Same as before. Okay. Personally, I find this to be the best approach, but this approach is correct as well. So if this works better for you, that's fine. If this works better for you, you can stick with this. But I thought I would mention this because we spent a lot of time working on unit conversions this summer. So anyway, you can always do this as unit conversion. So my point is anything that has fractional units can be used as a conversion ratio. Anything that has fractional units can be used as a conversion ratio. Remember, then there's two different ways you can write that conversion ratio. So since molarity has fractional units, you can always do molarity problems, or you can often do molarity problems as a unit conversion, using that as a conversion ratio. Like I said, this method is fine too. Okay, in any case, you did that correctly. Let's see. Okay, I think we got the basic idea then for that topic. So let's move on. The next topic we have to discuss is we have to make a digression into mathematics because a lot of the problems here deal with logarithms. So for example, let's say we have log x equals y. Do you know what a logarithm means? Do you know what's another? Do you know what? I don't know if you know what this means. Do you know what's another way to write this equation without the logarithm? I'm sorry. Are you saying something? I can't hear you.
No.
Okay. Go ahead.
Would it be an exponential form?
That's on the right track. So let's try to be more specific. What exactly could you write down that, and what's another equation you could write down that means the same thing as this?
Log base 10 of x would be 10 to the x.
Okay, so let's work on that. That turns out not to be correct. Did you have another idea?
I know it has something to do with the y. I don't remember.
Okay,
exactly.
This means 10 to the y equals x. This is what logarithms mean. So notice the way it's written is misleading. This does not mean 10 to the x. It means 10 to the y equals x. All right, that's very important. It's important to understand what logarithms mean. So let's try that again. How would you rewrite this equation without the logarithm?
That would be 10 to the b is equal to a.
That's right. Now, actually, theoretically, any number could be down here. This number is called the base. So what would this mean? How could you rewrite this?
It would be 3 to the power of d is equal to c.
That's right. Theoretically, any number can be the base. This number is called the base. But the only type of logarithm I think you're going to see in your biochem course is log base 10. So we won't need to worry about this. In fact, since they're all log base 10, they usually don't write the number. So you should keep in mind that if you see this, it means this. If they don't write the base, you should assume the base is 10. If the base is not written, you should assume that it's 10. Okay, you have this in your notes?
Yes.
So how could you rewrite this equation without the logarithm?
Ten to the x is equal to y.
Good. Notice I didn't tell you who the base was, so you just assumed that it was 10. Good. Also, let me show you a common mistake. Here's the wrong way to write this. Do you see that this is wrong? This is not what I'm saying here. I'm not saying that x equals 10 to the x equals y. We're not setting, you can't set two equations equal to each other. Instead, I'm using this symbol. This symbol means that this equation is the same as this equation. Equations can be the same, but they're not equal to each other. So you wouldn't want to write it like this. That's not the correct way to write it. Instead, what you do is you simply write a new equation without the logarithm. Okay? Let's see. So let's try to learn some basic properties here of logarithms. Maybe I'll go back to here. So let's try to understand some properties of logarithms. So again, how could you rewrite this without the, what's a new equation? How could you rewrite this as a new equation without using the log?
10 to the y is equal to x.
Good. Now let's try to investigate this. What happens when you increase x? If we increase x, is that going to increase or decrease y?
If you increase x, you're going to increase y.
How do you know? Well, I hope that you were trying to figure that out by using this. You can see from this equation what happens if x goes up. If you increase the right side of the equation by increasing x, you have to increase the left side. And the way to do that is by increasing y. So by using this, we can see that x and y, so do x and y move in the same direction or opposite directions?
Same.
Okay, so that's one basic principle of logarithms. The bigger the number, the bigger its log. It's kind of intuitive. The bigger the number, the bigger the log. The bigger the number, the bigger its log. Good? Do you know what this is? Now notice this 10 is not this. There's a 10 here in the base, and then there's this number. So this is, maybe I'll write it like this so it's clearer. Do you know what this is?
That is 10 to the, well, 10 to the power of 50.
Okay, looks like that's incorrect. So let's talk about that. First of all, so how would we work this out? Well, you could do it by writing a y here. We're trying to figure out y. Now, how could we rewrite this equation without the logarithm?
10 to the y is equal to 10 to the 5th.
That's right. This is the same. Notice how 10 to the 5th here is playing the role of x. Now 10 to the 5th is playing the role of x. So notice this does not mean 10 to the 10 to the 5th. This does not mean 10 to the 10 to the 5th. And now you should be able to solve this equation. What does y have to be?
5.
So what is the log of 10 to the 5th?
5.
That's right. So that's a way you can figure out a logarithm. You can figure out the logarithm like that. So what's this?
7.
Let's check that. How could you rewrite this equation without the logarithm?
10 to the y is equal to 10 to the 7.
If you don't know what the answer is, you put a y here, and then what does y have to be?
7.
So that shows that you did it correctly. Okay, good. So what we're seeing here is that logarithms are exponents. Logarithms are exponents. Logarithms are exponent. The logarithm tells you the exponent on the base 10. The logarithm tells you the exponent on the base 10. Good. What's this?
-3.
That's right. Let's check that. How could you rewrite this equation without the logarithm?
You would write 10 to the y is equal to 10 to the -3rd.
Good. Although since you already guessed what the answer is, you could write it like this. And now you can see your guess was correct because this is a true equation. You can see that your guess is correct. So notice this still works for negative exponents. The logarithm is just the exponent. Okay, good. So let's try to figure this out. Like this?
Wait a minute. So 10 to the y is equal to 10 to the first, y is equal to 1.
That's right. You could have made your life easier by writing this with an exponent from the start. What's the exponent on this 10?
1.
So you can see, since logarithms are exponent, this must be 1. Not 10. Try this.
Y equals to 0.
So what's the log of 1?
0.
Okay. So what equation did you write to solve that?
10 to the y is equal to 1 to the first.
Okay, that's right. Now, it doesn't really help to say it, call it 1 to the first. It's true that it's 1 to the first, but that doesn't help you to solve it. You could just say 10 to the y equals 1. And then what exponents does this have to be? Well, what is 10 to the 0th power?
1.
That's right. What's 5 to the 0th power?
1.
Yeah, anything to the 0th power is 1. So you did work that out correctly. Okay, good.
Just a side note, can you explain that? Like, why does something to the 0th power equal 1?
Rather than, so most people think it should be 0. Right. So why is it 1? Well, what does this mean?
5 times 5 times 5.
That's right. Does it mean 0 times 5 times 5 times 5?
No.
Does it mean 1 times 5 times 5 times 5?
No.
Does it?
It could.
So it does, basically, because they're the same thing, right? If you see what I'm saying? So is 5 to the 3rd equal to this?
No.
No. Is it equal to this?
Yes.
All right. So in a sense, you can think of 1 as your starting point. You started with 1, then you multiplied by 5 and 5 and 5 again. So in that case, how would you find 5 squared?
1 times 5 times 5.
The 1 is like the starting point.
Is that the right way to do it?
Well, it's a correct way to do it. Of course, you could just write it like this. This is correct as well. But for the purposes of our thought experiment here, this is more useful. So these are both correct ways. This is just more useful for thinking about it. Again, the point is, when you're multiplying, you have to start somewhere. And the logical starting point for multiplication is the number 1. For example, what does this mean?
5 to the first is 5.
5. Or, to follow our pattern, you
One
could
time.
call it 1 times 5. So following this same pattern, what would 5 to the 0 be?
1.
All right, so that's one explanation. Do you see how now this is the pattern? If we think that if we start with the number 1, so basically when you raise something to a power, what you really mean is that you're starting with 1 and then multiplying by 5 once or twice or 3 times. You're not starting with 0. If you started with 0, you'd never get away from 0, because 5 times 0 times 5 times 5 times 5 times 0 is still 0. So the reason that 5 to the 0 is 1 is because we haven't gotten away from the starting point, so to speak. The starting point for addition is 0, but the starting point for multiplication is 1. So that's one explanation, or maybe I can just give you another explanation if that seems a little bit weird. You could also write it this way. So you could say 5 to the third is 5 times 5 times 5. And now notice, how would you figure out 5 squared? You would divide by 5, right? If you took this and you divided by 5, you would get 5 times 5. Does that make sense?
Yes.
Now, if you wanted to find 5 to the first, you could divide this by 5. 5 times 5 divided by 5, that's 5, right? So now logically, since we got 5 squared by dividing this number by 5, and since we got 5 to the first by dividing this number by 5, logically speaking, to follow the same pattern, we should figure out 5 to the 0 by dividing this by 5. And what is 5 divided by 5?
Is 1.
Not 0. So I just gave you 2 explanations. So those are 2 explanations for why anything to the 0th power is 1, not 0. Now, ultimately, the real explanation is just that that's most convenient. It's just a definition. The mathematicians could have defined 5 to the 0 to be anything they wanted, but it turns out from long experience that this is by far the most useful definition. But we can kind of see why it might be useful or make sense by looking at it in terms of these patterns. Does that make any sense?
Yes.
Okay, now I did this with the number 5, but the point is you could do this for any number. You could also, this also gives you an argument for why 10 to the 0 is 1. Okay. All right, so let's see. In any case, hopefully that made sense, but obviously we should just also memorize 10 to the 0 is 1. If you want, I can't resist pointing out one more thing. What number is 10 to the third?
1,000.
1 followed by 3 zeros. What number is 10 squared?
100.
1 followed by 2 zeros. What number is 10 to the first?
10.
1 followed by 1 zero. So following that same pattern, what number should 10 to the 0 be?
1.
Now it's 1 followed by 0 zeros. So that's a third argument. That's a third explanation for why it actually makes sense for 10 to the 0 to equal 1. It actually fits the pattern. Okay. All right, so let's see, where were we? So what did we decide? What's the log of 1?
The log of 1 is 0.
We just proved that over here. That's probably something that's worth memorizing as well. All right, so continuing on, what's the log? I'm going to give you a trick question now. Here's the trick question. What's the log of 0?
1.
How would you try to figure that out?
Log base 10. Hold on. 10 to the y is equal to 0.
Now, would you agree there's no way to make this equation true?
Correct.
10 to the nothing. There's no number that you could put here, because if you 10 to any power will be positive. Whatever power you put up here, it's going to come out to be a positive number. So this was a trick question. This is undefined. There's no logarithm of 0. We just proved that because this equation is undefined. There's no number you could put here that would make this work. So it's good to know you can't take the logarithm of 0. You can't take the logarithm of 0. Here's another trick question. Here's another trick question. What's this?
Can I take the logarithm of a negative number?
How do we know? How would you rewrite this as another equation?
That would be 10 to the y is equal to negative 3.
But 10 to the y is always going to be positive. There's no way it could be negative. Okay, so it's good to know you can only take the logarithm of positive numbers. You can't take the logarithm of 0 or of negative numbers. Okay, let's try this problem. Now, this problem you can't do by hand, so now you'd have to use a calculator. But we could estimate this. Would you agree that this is going to be pretty close to -5?
Yes.
Because remember, the logarithm of 10 to the -5, what's the logarithm of 10 to the -5?
You can't take the log of a negative number.
Actually, I guess we're getting a little confused. You can't take the logarithm of -5, but this is not a negative number.
Oh. That would be -5.
That's right. So I might have confused you a little here. Remember the exercise that we did. Is this a negative number?
I don't know where you're pointing. Yes.
That's a negative number. Is this a negative number?
No.
No, it's not a negative number. What is it? It's a small fraction. This is a small fraction. So can you take the logarithm of -7?
Yes. The -7, no.
No, because you can't take the log of negative numbers. Can you take the log of 10 to the -7?
Yes.
Yeah, because that's just a small fraction. Okay. So what's the log of 10 to the -5?
-5.
That's right. I just wanted to point out, then we could estimate this. This is pretty close to 10 to the -5th. So we could estimate this will be close to -5. But we can't figure it out exactly without a calculator. So do you have your calculator with you?
Yes.
So go ahead and work that out on your calculator.
-5.
It came out to be exactly -5?
10, log base 10 to the...
Oh, I'm sorry. This one we already knew. So you just confirmed
Right.
this. Now I wanted you to do this one, which we can't do without a calculator. This problem here, if you can see where I'm pointing.
Yeah. That is -4.43.
So notice close, but not exactly equal to -5. So this type of problem, you need a calculator to figure out exactly, but we can at least estimate it based on the power of 10, is my point. Are you going to be allowed to use a calculator on your exams?
I think so.
Okay, you should definitely double check. That would be a good thing to double check with your instructor next time, but we'll assume for the time being that you can. We'll assume that you can use a calculator. So you can always figure out logs in the calculator. I think it's important to be able to do really simple logs without the calculator, just so you have a little bit of a sense of what you're doing. But any complicated log, you should go ahead and just use the calculator for that. Okay, good. Okay, so talk me through how you would solve this problem.
I would have 10 to the x is equal to 8.6 times 10 to the -3rd.
Okay, that's true. You totally could do that, but there's no simple way to solve that equation. That's now too complicated for us to solve. So even though that's true, that's not the best way to actually solve this. What I actually was going for is the way to solve this is just to use your calculator. Remember, the only logarithms I would expect you to be able to solve without a calculator are ones like this. This logarithm I would expect to be able to solve without a calculator. But when there's a coefficient, we should just go ahead and pull over the calculator. So how would that work here? Before you do that, though, give me an estimate. What would you estimate this log to be?
Around -3.
Because that's the exponent on the 10. Okay, good. So let's see what the calculator says.
-2.0655.
Okay, that's correct. So I explained to you this method of thinking about logs. Anytime you have an equation about a log, you can rewrite it like this. But that doesn't mean you always should do that. A lot of logarithms you can just solve using your calculator. So this is always legal, but it's not always helpful. We went over this so we could understand logarithms more carefully, but a lot of logarithms you can just solve on your calculator without rewriting it like this. You'll have to use your judgment to decide when it's useful to rewrite the equation and when we should just reach for the calculator. So talk me through how you would solve this problem.
It would be around -7.
Good. That's a good start. Then what?
Plug in the calculator. And I get -6.309.
Who is equal to -6 round that off more carefully.
-6.31.
Okay. What's equal to -6.31?
X.
Okay, good. You could also say the log is equal to that. Okay, good.
It always needs to be in parentheses, right?
Who has to be in parentheses?
The
You mean this number here?
Yeah.
I don't know. It doesn't necessarily, well, it's probably better just to be clearer. If you wrote it like this, yeah. Well, here it's probably better to put it in parentheses because otherwise it's not clear whether the 10 to the -7 is part of the log or not. On the other hand, if you were just doing this, here it's kind of a matter of taste whether you put in the parentheses or not. If it's just one number, you don't necessarily need the parentheses, although maybe that makes it clearer. Does that make sense?
Mm-hmm.
Okay. All right, talk me through how you would solve this problem.
Um, 10 to the 24th power is equal to x, so that would be a very, very big number.
So what's the answer to the question?
We have to plug it in the calculator. 10 followed by 24 zeros.
Right, or the answer is 10 to the 24th. This is a perfectly good answer right here. The answer is 10 to the 24th. Okay, well that actually was good. So I was trying to fake you out here by shifting to a different type of problem. Do you see how this problem looks similar to the previous one, but they're totally different? These two problems look kind of similar, but they're solved completely differently. This problem, we didn't really have to do any algebra because it was already solved for x. This was already solved for x, so there wasn't really any algebra to do. We just used the calculator. On the other hand, this problem, here's where you needed to use the trick I taught you about earlier, where we rewrite it without the logarithm. So like I said, you have to use your judgment to decide which problems you can just solve with your calculator and which problems you need to rewrite as a new equation without the log. So in this case, in this problem, we just needed the calculator. But in this problem, we needed to first rewrite the equation without the logarithm. And then we were pretty much done. Then that just told us what the answer was. Okay, good. Okay, so let's try this problem.
So 10 to the negative 3.7 is equal to x. So the answer is 0.0002.
Like this?
Yes.
Okay, excellent. Good. So in this case, you wouldn't want to leave it like this. You wouldn't want to leave it with a decimal exponent. You wouldn't want to leave it with a decimal exponent, so you used your calculator to solve it. Okay, so this is an important type of problem. So here's where we need to know how to rewrite logarithm equations without the exponent. All right, remember the biggest mistake people make here, this does not mean 10 to the x equals negative 3.7. This would be the most common mistake. Remember, this is not 10 to the x. It really is translated into 10 to the negative 3.7. So that's the biggest mistake to watch out for. Okay, well, I think that covers the key things that we need to know about logs for the problems that you were given. So let's move on. Okay, so let's go back and talk about now, so what is the solvent in the body?
The solvent is
For
blood.
the chemical reaction. What's the solvent that chemical reactions take place in the body?
Blood.
Okay, that's a good answer. What is the main liquid that blood is made up of, though?
Plasma.
That's a good answer. What's the main chemical substance, though, that makes up the plasma?
I don't know.
Not sure? You might know once I mention it. Maybe the question was weird, but the answer is water.
Oh.
Blood is mainly water. Cytoplasm is mainly water. You might have heard the saying that your body is like 70% water.
Mm-hmm.
So water is the most important molecule in the whole body. So, and that's what chapter 2 of your textbook is about. So let's look at an important reaction that water goes through. One of the very important reactions that water goes through is that water molecules spontaneously split into two pieces. So this is an important chemical equation that water goes through. Do you know what these symbols mean? This means this water is a liquid. What does AQ mean, though? AQ, it means aqueous, but what does that mean? A lot of students don't know what it means. It means dissolved in water. AQ means dissolved in water. So one of the water molecules has split, but there's still plenty of water molecules that haven't split. So these ions would be dissolved in water. We'd have H plus and HO minus. So these are very important ions. Do you know what the name of this ion is?
Hydronium.
This one I'm pointing to?
Hydroxide.
Hydroxide, yes. Now what about this? This is technically not hydronium. Hydronium would be H3O+. Hydronium is H3O+. What's the name for this? Well, a good name for this, this is a proton. H plus just means a proton. Let's make it a little digression so we can understand why that is. H by itself would be neutral hydrogen. Do you know how many protons a neutral hydrogen has? Do you know how many protons a neutral hydrogen has?
1 proton and 1 electron.
That's right. It has. How do you know it has 1 proton? Because its atomic number in the periodic table is 1. And how do you know a neutral hydrogen has 1 electron?
Because it doesn't have a charge.
Yeah, it needs 1 electron to balance the proton. So, what would be in an H plus, how many protons would H plus have?
1.
Because it's still hydrogen. All hydrogens have 1 proton because the atomic number for hydrogen is 1. But how many electrons does it have to have a +1 charge?
None.
So do you see, that explains why chemists use H plus as the symbol for a proton, because H plus just is a proton with no electrons. So H plus is a good symbol for proton. It really is just a proton with no electrons. Okay. Maybe I'll mention this equation is actually a little unrealistic. This isn't what really happens. What really happens is that the water creates hydroxide, and then this proton would attach to another water to form hydronium that you had mentioned. What really happens is that this proton would protonate water and form a hydronium. That would be more realistic. But it's common in biochemistry textbooks to be a little, to simplify and just pretend that you have H pluses. And that's what your textbook does, so that's what we'll do. So your textbook doesn't usually talk about hydronium. It simplifies and pretends that we just have protons floating around. So we'll do that too. That's an acceptable simplification. So here's the equation we'll be working with. Okay. So let's see. So how much is this going to happen? How much, if we have some water, how many protons and hydroxides are we going to have? Well, that's determined by the equilibrium constant for this equation. The equilibrium constant for this equation would tell us how many protons and hydroxides we're going to produce. For example, it's possible that 90% of the waters could split, or maybe only 50% of them will split, or maybe only 1% of them will split. The equilibrium constant helps us to figure out how many of these are going to split or ionize. Let's see. Do you know what the symbol is for the equilibrium constant for this reaction?
No.
So this symbol, you probably will recognize it when I write it down. The symbol for this reaction is Kw. So Kw, this is called the water autoionization reaction. Do you see why that's a logical name? Auto means self. Well, the water is ionizing itself by splitting into these two ions. Do you recognize, have you seen this symbol before?
I don't think so.
Oh, no? Okay. Well, your instructor should be talking about it in class anyway, when they get to chapter 2. In any case, so I'll tell you then that this symbol is equal to 10 to the negative 14. At room temperature, this is 10 to the negative 14. It's a convenient coincidence that this happens to be such an even number. This should be memorized. You need to memorize this. Kw is 10 to the negative 14. So we were trying to figure out before how many, when the water ionizes, how many protons and how many hydroxides are we going to get? When the water ionizes, how many protons and how many hydroxides are we going to get? Well, we can kind of figure it out. Do you agree that the number of protons will normally be equal to the number of hydroxides? Or let me put it this way. Do you agree that in pure water, the number of protons will equal the number of hydroxides?
Yes.
Because every time one water ionizes, it makes 1 proton and 1 hydroxide. So in pure water, the number would be equal. So if these, well, I'm getting a little ahead of myself. So we need to review how equilibrium constants work. So do you remember the idea of an equilibrium constant from chemistry?
Yeah, it rings a bell.
Hopefully it'll ring a bell. So the way you would write the equation here is you take the products and you write them on the top of the fraction. This is the equation for the equilibrium constant. Now, I don't know if you remember from chemistry, usually you would write the reactants on the bottom. Usually you would write the reactants, starting materials, on the bottom. But actually, I don't know if you remember this from chemistry, but you only include, you don't include any pure liquids in your equilibrium expression. You don't include pure liquids in the equilibrium expression. Since the water here is a pure liquid, it doesn't get included. only the aqueous species get included. So this is the equation for the Kw. This is the equation for the Kw. Now remember we just said that in pure water, these two concentrations would be equal. So we can call them both X. And what is Kw? What number is Kw?
Ten to the negative 14th.
That's right. That we should memorize. So now we need to solve this equation for X. So talk me through how would you go about solving this equation for X?
X squared is equal to 10 to the negative 14th.
Okay, good. Then what?
Can I square root both sides?
Sounds like a good idea. How would that work?
You get X is equal to 10 to the negative 12th.
Did you do that on your calculator or on paper?
It's 10 to the negative 7, sorry.
That's right. I think what you were thinking of is maybe something like this. This is how you would get 10 to the negative 12.
Mm-hmm.
Here you would subtract the exponents and you would get 10 to the negative 12, but this isn't square rooting. This would not be square rooting. If you think about it, we should kind of been able to do this in our head. We were trying to figure out what number multiplies by itself to equal 10 to the negative 14. Well, what is 10 to the negative 7 times 10 to the negative 7?
10 to the negative 14th.
How do you know? What do you do when you're multiplying two numbers with the same base? What do we do with the exponents?
You add them together.
And you would see that would give you 10 to the negative 14. So if you look at it the right way, you could kind of do this in your head. Okay, so what did we decide? In pure water, what's the concentration of protons?
In pure water, the concentration of protons is 10 to the negative 14th.
Actually, that's not correct.
10
Kw is 10 to the negative 14, but that's not the concentration of protons.
It's 10 to the negative 7.
Because notice we were using X here to stand for the proton concentration. And in pure water, what's the concentration of hydroxide?
In pure water, the concentration of hydroxide is 10 to the negative 7th also.
Because the X also stood for the hydroxide here. Remember, we were expecting that in pure water, the two concentrations should be the same. What are the units on these answers?
Kw.
10 to the negative 7 kW. Kw is not a unit, so that would be incorrect. My question was, what are the units? What's the units on this 10 to the negative 7? That's not something we can figure out from the equation, but we can figure it out from the brackets.
So yeah, it's the concentration would be molar. Or
It must be molar, yes. You can't work that out from the equation here because I didn't tell you what the units were on the Kw. But we know that any concentration is in molar. And what are the units on this number?
molar also.
That's right. How do you know? Just because brackets always means molar. Okay. You have that down?
Yep.
So what's the value of Kw?
Kw is equal to 10 to the power of negative 14.
Good. Something you should have been asking is what are the units on Kw? I forgot to mention that. This has no units. This has no units. In pure water, what's the concentration of protons?
The concentration of protons is 10 to the negative 7th. molar.
That's good that you put in the units. And what's the concentration of hydroxide?
10 to the negative 7th molar.
Now, you should be able to prove that using this mathematical equation here. You could prove that using this mathematical equation, but that should also be memorized. So what's the mathematical equation that we can write about this chemical equation? What's the mathematical equation that we can write about this chemical equation using Kw?
X times X is equal to Kw.
Good, except that only works in pure water. So take a step back. What's the general equation that's always true here?
The concentration of one atom, or the concentration of one reactant plus the
Well, now let's be more specific. Which reactant are you talking about? Maybe let me specify here. The equation I was going for was this one.
Oh, right.
This equation is always true.
Okay, so I can use that as a reference?
Yeah, that's always true. This equation with the x's is only true in pure water, because it's only in pure water that we can assume that the two concentrations are the same. So you start with this equation, H plus times hydroxide equals Kw. This is always true for this water autoionization reaction. Tell me when you have that down.
Yes, I have.
Okay. Okay, so again, to review, what is the chemical equation for water autoionization? What's the chemical equation for water autoionization?
The concentration of protons times the concentration of hydroxide is equal to Kw.
Okay, that's the mathematical equation. That's right, although that wasn't quite what I was going for. But that's right. What's the chemical equation for the autoionization reaction? A chemical equation has starting materials and products. What are the starting...
H2O, and then an arrow.
In liquid form.
And then you have proton, aqueous, plus hydroxide, aqueous.
Okay, so this has to be memorized too. This is the chemical equation. And this is the mathematical equation. We know that in pure water, H plus will be the same as hydroxide. But if it's not pure water, there could be different amounts. So let's see how these are related to each other. Let's actually take this a step further. We can be a little bit more specific here, because what is Kw?
10 to the negative 14th.
So we could write that. Now, let's say that we increase the H plus concentration. What will happen to the hydroxide concentration?
It will also increase.
How did you figure that out?
Because they're multiplied to equal a number. So if one goes up, the other must go up.
Is that true? So
No.
if this gets bigger, we know that the product still has to be the same. It still has to they still have to multiply to equal 10 to the negative 14. So if this is getting bigger, what has to happen to hydroxide so that they still multiply to give 10 to the negative 14?
It has to decrease.
All right, so it looks like our first answer there was mistaken. So does the proton concentration move in the same or the opposite direction as the hydroxide concentration?
Opposite directions.
That's going to be very important. Very important that proton concentration moves opposite to hydroxide concentration. You can see that from this equation if we think about it clearly. It's just like, suppose you had 2 times 3 equals 6. No, let me try this. Let's say you had 3 times 4 equals 6 times 6 equals 36. And let's say I lower this number to, let's say I increase this number to 9. If you increase the first number to 9, what happens to the second number?
The other number has to go down.
To 4. That's right. So the same thing is happening here. These move in opposite directions from each other.
That makes sense.
So what would happen if we decreased the proton concentration? What would that do?
Increase the hydroxide increase.
That's right. What would happen if you increase the hydroxide concentration?
You have to decrease the proton concentration.
That's right. In pure water, what is the proton concentration?
10 to the negative 7th.
And what's the hydroxide concentration?
10 to the negative 7th molar, sorry.
Yeah, that would be a better answer.
So there would be 10 to the negative 7 moles per liter of water. There would be 10 to the negative 7th moles of protons in 1 liter of pure water.
Excellent. That's a good way to make it concrete. Yes. So that's very practical. If you pour yourself a liter of water out of your sink tap, if you turn on your sink and pour yourself out a liter of water, that liter of water, if you could count it, would have 10 to the negative 7 moles of protons, and would also have 10 to the negative 7 moles of hydroxide. By the way, the big thing to notice is, are these big or small numbers?
Very small numbers.
So does water ionize a lot or a little?
A little.
Only a little. So that's something I remember I mentioned earlier, that theoretically 90% of the water could ionize, or 50%, or 1%, but it turns out that only a tiny, tiny fraction of the water is ionizing. A tiny fraction, far less than 1%. Only a tiny fraction of water ionizes. A tiny fraction that's far less than 1%, because this Kw is such a tiny number. So we were just saying that only a tiny fraction of the water ionizes. Now, let's say that we have not pure water. Let's say something's been added to the water so that the H plus concentration is greater than 10 to the negative 7. If H plus concentration was greater than 10 to the negative 7, what could you predict about the hydroxide concentration?
The hydroxide concentration would be lower than 10 to the negative 7th.
Yeah, it started at 10 to the negative 7, and then it had to get smaller when we increased the H plus. This type of solution is called, do you know, is this called an acidic or a basic solution?
Hold on. It's acidic.
Because acidic means a lot of protons. An acidic solution has many protons. So this would be an acidic solution. This is not pure water anymore. This is water that an acid has been added to. So what's another name for pure water? Pure water then would be a neutral solution. Suppose that the H plus concentration was less than 10 to the negative 7. What would you predict about the hydroxide concentration?
It would be basic.
This would be a basic solution.
And the hydroxide concentration would go up.
So what,
greater than 10 to the negative 7.
Because it started at 10 to the negative 7 in pure water, And then if you lower H plus, you have to increase HO minus. So they still multiply to be 10 to the negative 14. So tell me when you have this table in your notes.
Okay.
All right, so this is an important table to be familiar with. Okay, here's another problem. So copy this down, and then when you're ready, talk me through how you would go about trying to solve this problem.
So I would have 3.10 to the negative 9th times x is equal to 10 to the negative 14th.
That's excellent. That's a great start. Before we do that, let's try to predict what range our answer is going to be in. Any prediction you can make here before you use your calculator and before you use the math?
I would say that the answer would be around 10 to the negative 5th.
Good. So are you predicting an acidic or a basic solution?
I am predicting that it would be a basic solution.
What was your thinking there?
Because there's a higher, or actually a basic solution. No, I'm predicting it's going to be more acidic because there is going to be a higher concentration of protons than hydroxide ions.
Right. The easiest way to see that is, remember, what would be the hydroxide concentration in a neutral solution?
10 to the negative 7.
Is this bigger or smaller than 10 to the negative 7?
Smaller.
Smaller. So does this have relatively high or low hydroxide?
Relatively low.
So should it have high or low acid, high or low protons?
Higher protons.
Yeah. So that's the way you could work it out without really doing any math. So we expect this to be an acidic solution. Okay. So what was the equation you were using again?
10 3 times negative 9 x is x to 10 to the negative 14.
Good. I would just suggest, what does the x stand for?
X is the concentration of proton.
So why don't we just call it that? There's no need to use x. It's better to use a symbol that stands for what it really means. In fact, we could start with this equation. It's always best to start with the most general version of the equation. So here's the most general version. And then you could plug in 10 to the negative 14 for Kw and 3 times 10 to the negative 9 for HO minus. But there's no need to plug in x for H plus. We could just call it H plus. All right, what then?
Then divide by 3 times negative 9.
Okay, good.
That's my good. 0.0
0.00003. So 3 followed by or decimal followed by 5 zeros and then 3.
So what's the answer to the question?
The answer is the concentration is 10 to the 3 times the negative fifth power.
Now, the most important thing here, we would not get full credit for that because we didn't include units. In science, we always have to include units on our answer.
So molar.
Molar. Okay. So you tried to put this into scientific notation in your Now, you don't have to put it in scientific notation. You could just say this is the answer. What type of calculator are you using?
The TI-CX.
Okay. Yeah, so there's probably a way to change the settings so it would put that number in scientific notation for you. I'm not sure what that is. In any case, the way you do this is, how would you do that? The key is, where is the decimal point in this 3? If you don't write the decimal point, where is it?
The decimal point is to the left of it.
Here?
Oh, no. In that one, it's to the right.
So 3 really means 3 point. Now let's see if this would work. If you move this decimal point 5 places to the left, would you get this number? This is something to work out on paper, not on your calculator. If you take the decimal point from here and move it to the left 5 times, will you get this number?
No, you get
So this is not correct. What should this exponent be?
-6.
Now, if you take this decimal point and move it to the left 6 times, would you get this number?
Yes.
Okay, so it's good to know how to change things into scientific notation and back and forth by hand. Notice you probably said 5 because there's 5 zeros here. There are 5 zeros, but this doesn't count the number of zeros. It counts how many times we're moving the decimal. The exponent counts how many times we're moving the decimal, not the number of zeros. Although you could get it work if you wrote it like this. Your calculator actually probably gives you the answer like this. If you include this 0, then the exponent does tell you the number of zeros. So that's one good argument for including that 0. Okay, so what was the answer to the question?
The answer to the question was 3 times 10 to the -6 molar.
Is the concentration of H+. Did that match our prediction? You were predicting it would be close to 10 to the -5th. This is close to 10 to the -5th. And you were predicting an acidic solution. Did we get an acidic solution in our answer?
Yes.
Because it's bigger than 10 to the -7. Okay, so this is an important type of question here. So you basically understood the method. You understood to use this equation to solve this. Good. Okay, so write this problem down, and when you're ready, talk me through how you would solve this.
I need to leave after this problem.
Okay.
Okay, so we have bracket proton times the bracket with hydronium.
With who? Right.
Hydrox is equal to KW.
Excellent. That's a great start. But before we go to the math, what would you predict about your answer without doing any math?
That it would be a highly basic condition, or highly basic solution.
Good. Because we know this number, is this number bigger or smaller than 10 to the negative 7?
That is much smaller than negative 7.
So we know it's basic. So the hydroxide concentration is bigger than what?
The hydroxide concentration is around 10 to the negative 30.
Okay. I was going to say, we know it's bigger than 10 to the negative 7, but you can go a little bit further and do in your head and see it's going to be much bigger than 10 to the negative 7. Okay, good. So let's continue with the math. What now?
I have 8 times 3 or 8 times 3 times the negative 11 times bracket hydroxide is equal to 10 to the negative 14th. Divide both sides by 8, 3 times 10 to the negative 11th. And then we have hydroxide concentration is equal to 0.00012 molar.
That's very important to put in those units. Good. All right, so that's correct, and that's consistent with the answers that we were getting earlier. The first part of the course here is really kind of a review of acids and bases from general chemistry, but I think you might have forgotten a lot of that material. So we actually didn't get today to anything that was as hard as the review problems you sent me. We had to go over kind of some preliminary material, so we're not really ready yet for those. We didn't get to the actual review problems you sent me, so we have quite a bit of we got quite a bit of work left. So it's important to really carefully review this material so we don't have to review this next time. We don't want to spend too much time on review. We want to move on to the new stuff because there's a lot of stuff left for acids and bases is actually pretty time consuming to cover because there's many different cases. So anyway, like I always do, I would strongly recommend really carefully review the problems that we did together today. Redo these, make sure these are all easy for you so that we don't need to spend time on review and we can try to get to as much new stuff as possible.